Okay, so we've got a rocket that it's 122 kilograms, right? And it burns fuel at a rate of 3.45 kilograms per second for 23 seconds. So let's figure out how much fuel it burned, right? That's going to be the mass of fuel is going to be 3.45 kilograms per second times 23 seconds. This is rocket science, so it is hard. 3.45. Okay, times 23. 79.35 is fuel, right? That means that the initial mass of the rocket, the initial mass is 122 kilograms. And the final mass of the rocket is 122 minus the fuel. So 122 minus that number is 42.65. So you got to figure out the initial and final mass of the rocket, okay? Then it turns out most people mess up not there. People mess up on this next step here. Let's find the force, right? The thrust of the engine. So force times time is mass delta V, okay? Now, remember that this mass has to be the mass of the fuel burned in this much time. So I could either use 79.35 kilograms of fuel in 23 seconds, or I could use 3.45 kilograms in 1 second. It doesn't matter which, because they're the same ratio. There's only a factor of 23 in the numerator and denominator difference with this, okay? So I choose to use the 3.45 in 1 second because that makes my math easier. So the force times 1 second equals 3.45 kilograms times 772. So basically, the short version of this is if you multiply the mass burn rate by the exhaust velocity, you get the thrust. That's it. Okay? So 3.45 times 772. That's a lot of thrust. That's 2663.4. Now I assure you, if you put in 23 seconds and 76.35, you'll get exactly the same answer. Okay? So you don't have to do it, but I mean, go ahead and do it. It's because of maths. Okay? So first step, I think, is find the masses. Second step, find the thrust. But do it correctly. I think people just throw any mass in here and hope they get the right answer. It's got to be the mass of fuel. This has to be the mass of fuel burned, and this must be the time it took to burn that fuel. Okay? And now we just have to figure out the accelerations, right? So we'll do the initial. So initially, the weight, the force of gravity, right, is 122 times 9.81. So initially, the acceleration will be less because for two reasons. It's got more inertia, but it also has more force of gravity acting on it, right? They're different things. But both of them are just because it has more mass. So that's the force down, right? And then let's figure out the final acceleration. Okay, so for the final acceleration, the force of gravity is going to be that final mass. Remember, this is rocket science. How can I expect you to do it? 9.81, so 42.65 times 9.81, 418. Okay, now we can set up, the Newton's second law. So this is going to be the upward force for both of these guys. Here the downward force is this guy. So there's more weight. There's also more inertia here, right? We're dividing by a bigger number. Okay, so let's do this. 2663.4 minus 1196.82. That's 1466.58 divided by 122. And that's 12.02. So 12.0 meters per second squared is our stately initial acceleration. Right? Okay, and then basically, like the model rockets I had, they took off like a bullet. You couldn't see them, except for like the big ones, right? Okay, so here we have the same thrust. We're going to assume that the engine doesn't warm up and generate more thrust, but it does. Okay, minus, and then it's going to be less weight, less force of gravity. And less mass, 40. Okay, so let's do this. Let's see. Where is it there? Minus, so 2663.4 minus the 418 number. That gives me 2245.0053, and then divide by the 42.65 number. I'm so lazy. I'm using the up arrow on my calculator. I don't know why. There it is. 52.6. So this might not be a manned or womaned mission. A person. It will not be a personed mission, because that's a bit much upward acceleration. Keep in mind that you would feel 1g more than that, because you feel 1g for free. So you'd feel about 6g's, which for a long time like that might be too much. Maybe they could withstand it, though. I don't know. All right. Woohoo!